my name is Ana Sofia Aguilar, and I'm gonna start exposing the background of our telescoping boom truss design that was required on our mechanical design class at New Mexico State University. Project motivation and objectives. An engineering company of telescoping boom trusses for conveying trash rock and other materials wants to consolidate their line by innovating their designs to meet specific requirements such as overhang reach, elevation, and maximal load. As a team, we are responsible to create the overhang design concept, selection of materials, and measurements to come up with a final design that works safely and efficiently. Problem statement. The company's specifications for the design were to be able to have an overhang ridge that can convey the loaded material between 50 feet and 100 feet. The elevation of the truss should be between the ranges of 10 and 50 feet. The maximum load allowable to convey needs to be 7.5 tons, but the total weight of the telescoping truss must be less than 25 tons. Other requirements had to be with the material selection. Must be able to operate 12 hours, and the desired life has a minimum of 10 years. Of course, the main problem is to meet all these requirements and make them fit with the lowest cost possible. Safety is an unquestionable requirement.
All right, so the background of this project is the application to a lot of different engineering processes, including things like mining, dirt processing, mulch processing, asphalt moving, and other hauling of such loose materials. Such boom truss systems would be extremely useful. Important engineering design techniques that were employed in this project include material selection, stress analysis, failure analysis, and other important engineering considerations.
For our design, we decided to go with the how truss for the base and extending component of our model. The hydraulic system will include a cylinder which extends from 22.75 feet to about 28.5 feet length at a minimum degree of 9 degrees and a maximum angle of 60 degrees. We use ASTM A992 steel.
And for our design, we also created a 3D model, which you can be able to see here. The 3D model can move and it can spin. And extend and contract. And this was to do for the purpose of extra credit. Okay, so our design variables. So design variables are things like, weight and the cross-sectional area, and they're variables that we can manipulate and change. In our specific one of our design variables that we took into account was the type of truss we wanted to use, because this would determine the force in each member and change the force in each member based off different trusses. We decided to go with the how truss as it had been used throughout several hundred years and was used with wood structures before, meaning it can handle a lot of load and not equivalent to a lot of stress within each member. As well, another design variable was the cross-sectional area, and we had 3 different cross-sectional areas to help reduce the actual loaded members, the stress in the actual loaded members, to increase our factors of safety.
For our model, we went with a fixed exterior truss final design that had measurements of 8 foot height, 8 foot width, a cross section of 3 inch thickness, and the total length of this was about 84 feet length. The inner truss, which extended the overall reach of these measurements, was 7 foot height, 8 foot wide, and 54 foot long.
The static study was done through a website on JHU, and basically you could design your own truss and be able to analyze the forces in each truss member based on the distributed load on the top. In order to do this, we had to calculate what the X component and Y component of force would be. And we also had to calculate where the reactions would be. The first figure shows the second truss under a distributed load at a full extension. So there's reactions at the far left component, and at the far left node and the second far left node. The second figure shows the base truss and has reactions at the middle where the hydraulic system is, and the far left where the base of the material is, or the base of the truss is. Stress analysis. So basically, in order to calculate the stress in a truss, we had to use the actual stress formula, which is just force divided by area. Since a truss distributes all types of moments and loads to axial forces, this is why we only needed to worry about this formula. In doing so, we were able to also determine the factor of safety, and it helped to determine cycles in design life.
Hello everyone, I'm Julio Marin Bustillos, and I'm gonna explain the deflection part for the whole structure. So since the structure has to carry the 7.5 ton weight, we converted that to pounds, which is 15,000, and we assume this is under the distributed load. So we divided it by the whole length of the whole structure, which is 130 when it's fully extended. So as you can see right here, after making that division, we get a value of 115.4 pounds over feet. And we divided the structure into two trusses or two beams. In this case, we assume it's a beam, since for the analysis we believe it behaves, and for deflection it believes as a truss can behave as a beam. So for the first truss, since it is 6 feet, for that part we get a load of 76.34 pounds over feet. And we also added a pin reaction so that it can simulate the push arm. And after doing some research on the formula for the maximum deflection for that beam under that certain condition, we found that the maximum deflection is equal to the load times the length to the fourth over 185 times the Young's modulus times the second area moment. So for this particular case, we used A992 steel, and we got a value for Young's modulus of 41.76 times 10 to the 8 pounds per square feet. So then we calculated the value for second area moment, which is 1 over 12 times 86 times 8 to the 8 cubed, and we got this value. So after we got those two values, we plugged them into this formula, and we got a value of 1.76 times 10 to the negative 5 inches. And to see if this is safe to use or not, we divided the whole length in inches over 360, and we got a value of 2.88 inches, which is greater than our value for maximum deflection, which means that the beam is safe to use under that load. And we kind of did the same for the second truss. So for 44 feet, we have to apply a load of 39.06 pounds over feet. However, in this case, it's just the fixed condition. We don't have a pin. So we got this formula for that, which is load times L to the fourth over A times E times I. In this case, Since we're using the same material for the whole structure, we use the same value for E, and for I, we got this value, which is 792 feet to the fourth. And again, after plugging in all those values, we get 6.6 times 10 to the negative 5 inches as our maximum deflection. And after dividing the length over 360, we got 1.47, which is also greater than our value for maximum deflection, which means that the structure is safe.
Right. In our analysis, we considered static and dynamic loading, although mainly static loading, as we assumed that even though the dirt and other loose materials were moving, the overall loads would continue to be uniformly distributed on the truss system and thus be a static load. And so for the truss system, we mainly considered static failure. As far as dynamic failure, we left that more to the mechanical part of the design for the rollers and the motors and the hydraulic systems, as those would be subjected to dynamic loads and would need to have their expected life considered in order to fulfill the design requirements. Finally, like we mentioned, we did failure analysis. Failure analysis was using von Mises stresses on the truss. And since it was a truss and thus a two-force member, the von Mises were equivalent to the axial stress. And so we were able to calculate our factors of safety by comparing these axial stresses to our yield stresses and get our factors of safety, which we all found to be greater than 1, meaning we had a safe system. Thank you all for taking the time to listen to our report.